Right. Hello. Right, so this is quite a broad subject, so I'm not going to go too much in depth at any one point. I'm just going to go through the applications and the modeling as a whole. And if you have any specific questions or you'd like a more in-depth conversation, I'd encourage you to contact me afterwards. So the general rationale for GPU modeling is when you have a problem that is computationally simple, but quite wide, so it's easily separable into different parts that can be solved individually and then combined at the end into a wider problem. Just to give an example, the model that I wrote for doing antenna array analysis during my PhD was a CPU single-threaded model, and it took days of computation for the scenario I was interested in at the time. When I moved this over to the GPU, fairly simplistically, the same scenario took hours. And with my current generation of GPU model, where I've actually taken a bit more advantage of the architecture, the same thing takes place in seconds. And there's still quite a bit of overhead to that I can get rid of as I go along. The way that the model actually works at the moment is two recursive loops. The first is this one on the left of ray launching, triangle intersections, and recording those hits and creating what is effectively a network graph of the scattering in an environment. And then this graph is then passed to the electromagnetics engine, which simulates illumination functions, propagation across this graph, excitation functions as things scatter off the environment. And then each cycle keeps going recursively for as many scatters as are necessary. Now, one of the primary uses of this model at the moment is frequency domain scattering, which we have been looking into for over-the-air characterization of different devices for 5G and 6G. As we start to move up in frequency, the influence of the antennas or antenna arrays in these devices needs to be quite carefully measured, so we can make sure they're meeting the performance goals to fit in with the mobile networks. And we did some wideband measurements of a number of different types of reference and prototype reflectors from 20 to 26 gigahertz. And my co-author, and this was published in UCAP 2021, and my co-author did some very nice laser scans of some of the reflectors to give us a good idea as to what the ground truth actually was on the geometry of these things. And what you can see on the left here is one of the reference reflectors, which was a cast aluminium tooling plate. So it's provided with a certificate, giving a really good idea as to how flat it is across its surface. And on the right is one of the prototype reflectors that we were originally using, and it actually has a total height variation of 2.73 millimeters from one side to the other. That's about a fifth of a wavelength. So not really big, but still quite noticeable. And when we actually measured these reflectors in the anechoic chamber, what we actually got was that the prototype substrate reflector was 3 dBs down on the reference one. So a total height variation of less than 3 millimeters equates to half the power being reflected at maximum compared to the reference. And when we compare it to the GPU model, which is in green here, we can see a very nice agreement between the reference reflector and the model itself. And also the substrate, after it's gone down to sort of a lower, more diffuse scattering. Also something to note is that this kind of frequency of model implies about 2,300 surface points. And for each step, that's about 23 million rays going from the meshed aperture of the transmitting horn through the reflector to the meshed aperture of the receiving horn. And yet this kind of scenario now with the current generation of model is processed in seconds, about 2 seconds if memory serves. Looking at it on a statistical basis, we measured a number of different reflectors, and it was quite interesting to note that the effect of that warpage of the substrate effectively halved the area. So when we compared to a small reflector, which was also cast tooling plate and was half the area of the substrate reflector and the medium reference. We have the same in the normalized maximum, and it's really quite interesting to note that a comparatively small warpage in terms of wavelength, so only about a fifth at that frequency, equates to halving the size of the reflector. And when we compare the reference plates to the model, which is modeling a perfectly flat reflector, we get an RMS error for the small reflector in its model and the medium reflector in its model of minus 69 dBs, which is really quite satisfying level of agreement of predictive power for the model. Now, frequency domain is all very well, but what you really want for 5G and 6G is the ability to do a time domain model so that you can have a really wide band system. And so, of course, one of these things that was developed here is a time domain version of this same model. So it's still using the same architecture, still using the same raycasting engine, but the secondary, the electromagnetics engine is not just frequency domain capable, but also time domain capable. And you can see here, I was using a 10 nanosecond pulse to investigate this exactly the same scenario. And you can see that what's happening physically as that plate is being rotated around. The timing distance between all the pulses coming in and bouncing off the scattering plate and into the receiving antenna is getting smaller and smaller as it approaches that normalized maximum scattering angle. And it's really quite satisfying to see this kind of result. This hasn't actually been published yet, so this is seen for the first time here anywhere. Another thing that is being investigated with this kind of model is novel propagating modes like orbital angular momentum, which are mutually orthogonal modes that you can, in principle, stack on top of each other. So you can have zero order modes, plus minus one, plus minus two, up and up and up. And the idea about this is that you can have very high spectral efficiency and incredibly high data rates. And you can see here on the right, we have the phases at the same physical points of a conventionally phased antenna array, just causing ripple as you have the main lobe here, and then ripple as you go through the first side lobe, second side lobe. And then here we have an OEM mode of +1, and you can see this characteristic swirl of the OEM mode itself. And as you move away from the array, you get exactly the same kind of swirl. This is this behavior that leads it to be termed vortex modes. Now, this is that same mode in terms of amplitude in the far field, and you can also see the problem with OEM modes when you're attempting to use them for communications in free space is that there is this null on boresight, and as you go up to higher order modes, the null gets deeper, and the donut of maxima, it actually spreads out further and further. So as you stack on these higher order modes, you get less and less received power at your receiver. And I included here a quick model with this same approach, showing the difference between a conventionally phased set of arrays and OEM phased set of arrays in terms of the received the signal to noise level as it goes across a 4-kilometer track. And you can see quite clearly that at the maximum of the range, there's this 20 dB gap between the OEM and the conventional use of these arrays. And it's really quite a hill for OEM applications to climb to work out what's the right way of taking advantage of this kind of mode efficiency without losing out on the signal power. Now, this model started off life during my PhD as a way to try and lower the technical and financial risk of conformal antenna array design, supporting development, because I believe then, and I believe now, that there are a whole range of applications that really can benefit from cheaper, more accessible antenna array design. And really what I've really changed the stance to is that actually this is applicable to all antenna arrays, planar or conformal, whether you're looking at applications really in the near field like medical imaging, or very high frequency things like millimeter wave radar for border security, distributed apertures for things like astronomy, looking at really quite far away things with very dispersed apertures. One of the things that really can help the design is being able to predict its performance with a minimum of investment, a minimum of design effort. And so the first thing to do was to look at whether there was a way to predict the performance envelope of an antenna array without that design effort. And indeed, there is aperture projection. If you project the aperture of an antenna array with this kind of modeling approach, you can work out what the maximum directivity envelope is for that aperture at a given frequency. And that's when it's been beamformed and when you're steering it around in the far field. And you can see here an example of the maximum directivity envelope for this array in blue on this UAV. You can see the shadowing effects, and you can see the area where it's more easy to steer the array. And this by itself is useful, but when you add a little bit more to the model, you can get so much more out. So the next step was saying, well, if I actually model it as a antenna array, I use polarization. So a mesh of electric current sources going across the entire aperture. That means that we can use the same frequency domain model to produce an antenna array far field, which is shown here. And again, that's an interesting and actually useful thing to show, showing the effects of polarization on the far field. But then we want to go a little further. We need to add beamforming. Using this same kind of approach to add in different beamforming algorithms, different architectures, whether it's a fully analog architecture, whether fully digital, what sort of amplitude and phase resolution you're thinking about. All these things can be looked at, whether it's for near field scenarios like medical imaging, as I've got here, or that same UAV, but now beamformed. So this is the total directivity, the main beam directivity, as it steered each one of the possible far field points. And so again, you have this opportunity to look at all the different factors around your design without investing, because at this point, all you've actually got to work with is a frequency, a polarization, and you're looking into different architectures, you're looking into different algorithms, all without doing anything particularly intensive in terms of design. And the model for this, for most of these kind of scenarios, runs in seconds on a desktop computer with a GPU. So it's very convenient, very quick. The beamforming at the moment takes a little bit longer. But that's because I haven't moved the beamforming algorithms to the GPU as well. So at the moment, they take a little bit longer. Also, it's becoming much more interesting at 6G and 5G as we talk about these in-building networks to be able to predict multipath propagation characteristics across a building as a whole, across a city. And also of cars, when we're talking about driverless cars, things like that, we want to know in reduced visibility conditions what is actually out there on the road. And so being able to predict the electromagnetic scattering of comparatively large objects is a significant interest as we kind of develop this technology. And of course, this is some of the sort of things that are interesting to me as well, is looking at these effects. And this is the sort of thing that time domain scattering especially can be quite interesting in helping to understand these problems and to be able to apply the effect of this kind of model. So really one of the things that's interesting to me is as models get faster, they open up applications that were never possible before, when these models would take hours, days on this kind of scale. And so as models get more efficient, they can be applied to more and more things where the time scale is important. So I'm really quite interested with sensor fusion, where you take things like LiDAR output, time of flight sensors, computer vision, and using those to develop a model of the environment, which can then be passed to this Lycean EM, the model itself, and that can predict what kind of returns your antenna array might expect from the environment. And this can be done to do reference measurements. So we're looking at, the effects of windows on mobile phone communications or different architecture. But also things like surface cancellation. So one of the biggest problems for medical imaging with microwaves, which otherwise is a very promising, very interesting technology to me, is that the loss of skin reflection is very significant. And so in order to do something about that, you need some way to cancel out that reflection. And this kind of surface cancellation, where you have a very efficient, very fast model taking the output of LiDAR or computer vision sensors, predicting what that reflection is going to be, and allowing that cancellation, could improve the sensitivity and the usability of this kind of technology. Also, of course, things like ground penetrating radar for archaeology, searching for aquifers, looking to probe soil substructure in terms of new building projects, things like that. And also, we talk about 5G and 6G, more efficient mobile communication. So when you need very dense cell towers in built-up locations, the idea of when you install that tower, doing a very quick site survey with a camera or a LiDAR, and then in having that information in the cell tower itself, so it can become an intelligent node that knows where the major scatterers are in its environment, because it's able to run a very efficient propagation model and able to go, okay, well, I know that there are scatterers over here. And so in order to serve my customers that are about the cell here and also not interfere with my neighboring cells, I can steer in this fashion and really try and conserve energy while also offering the maximum data rate possible to the customer. Also, things like accident investigation is an interesting area where you have things that might not be visible to the naked eye, but to a radar, it becomes much more obvious. So if you can fuse these things together on really short timescales, you have the opportunity to help kind of characterize the environment with things like augmented reality in a very interesting way, and something that's also quite useful. And all these things are possible with the current model, but in the future, there's a hope to move from Python and Number, which it's implemented in the moment, to C++ and optics, which is probably about 200 times faster than my current implementation. And it's much more memory efficient for very large environments, which means it's much more possible to add things like cities as opposed to buildings into the memory environment itself. Now, if this sort of thing is interesting, I would encourage you to go have a look at my website examples, and also to come into the questionnaire with any questions and contact me afterwards.